Okay, kids, so we're back. We're on our way into chapter 8 here. I asked you to do some magnetism review yesterday. I hope you did that. I hope you enjoyed those videos again that we watched back in grade 11. Today I'm going to assign you some reading out of 8.1. 8.1 is all review, so it's another chance to get caught up on the stuff we learned in grade 11, so I strongly suggest you read through 8.1 once again to refamiliarize yourself with the whole idea of magnetism. And now, after you do that, we move on to 8.2. Now, there's going to be some reading from 8.2, some questions from 8.2. There's a couple of simulations we're going to look at, and then there's a video introducing us back into magnetism as we move forward here. Okay, so let's get started. So 8.2 is all about magnetism having a force on a moving charged particle, which is nothing really new for us because in grade 11 we noticed that when a wire had a current in it, and a current is nothing more, nothing less than charged particles confined to be in a material, usually a copper wire, that when the current was moving through that wire, the wire moved. I don't know if you remember this demonstration from grade 11, but that's what happened. The wire moved when there was a force. And depending on the direction of the magnetic field and depending on the direction of the current, the wire would either be pushed one way or in the opposite direction. So we're now in grade 12, we're going to take a mathematical look at this. In grade 11, it's like, ooh, look at the wire move. Ooh, piece of candy, right? And now we need an equation. We need to do some math. We're in grade 12. So A, B, B stands for magnetic field. Notice it's a vector field. There's a magnitude and a direction to it. And from grade 11, we learned that magnetic fields have a direction to it. We used our right-hand rule. We learned that it leaves the north-seeking pole of a barred magnet, enters the south-seeking pole of a barred magnet, all those things we learn in grade 11. It's a vector. There's a direction. So a magnetic field will apply a force on a moving charged particle. And we have an equation for that. The magnetic force vector is equal to the charge, and then that charge is multiplied onto the velocity of that charged particle. And then we do a special type of multiplication with the magnetic field. So Q is a charge, V is the velocity of the particle, B is the magnetic field that the particle is experiencing, and the particle is in this magnetic field. That big S right there, that big S right there, X right there, I should say, that big X right there is known as a cross product or a vector product. Goes by both names. I think you're familiar with this perhaps in your vectors course. Let's take a look at the units. So the unit is a Newton. And over here, we would have a Coulomb and meter per second. But we don't know what the unit for magnetic field is. Well, if you take a look at these two units here, Coulomb times meters per second, that would have to go in the denominator. And then the magnetic field's force would have to be a Newton over that. Now let me show you why that has to be true. Take a look here. If you have these two right here, and then you multiply it by that, right? Coulombs, meters per second in the denominator. Look, cancels, 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 and you have Newton left. And you want to have Newton left because when you multiply these all together, it's got to be equal to a force, a Newton. So that means the unit for a magnetic field is literally a Newton over a Coulomb meter per second. That's what it is. That is the unit for a magnetic field. It has to be that so that when we multiply through the charge and the velocity, we end up with a unit of a Newton for the force on the left-hand side. Now, they have named this unit. they have named this unit. And this unit is the Tesla. That is what the name of this unit is. It is the Tesla, named after a great scientist. So we need to investigate this. We need to investigate this force magnetic, this unit Tesla, how we actually do a cross product, so we can figure out how to move forward. All right then. Well, the first thing we have to do is be able to find the magnitude of the magnetic force on a charged particle. The magnitude of it. Well, that is done by doing this. It is equal to the magnitude of the charge that is experiencing the force, the magnitude of the velocity of that charged particle, the magnitude of the magnetic field that charged particle is experiencing, multiplied by the sine of an angle theta, where theta is the angle between the velocity of the charged particle and the magnetic field. It's the angle between them. Now you have to remember something about sine. The sine function has a minimum of 0 and a maximum of 1. That's how a sine function occurs. It goes 0, 1, 0, -1, and through. All right, you all know the sine function. It kind of looks like this, right? So, like that, right? The sine function. 0, 1, 0, -1, 0. Those are its maximum values. So, how do we get the direction of a magnetic field? That's what we're going to look at next. So we're going to learn this by an example. So let's say you've got this charged particle, Q, here it is, and it's out here where there's no magnetic field. No magnetic field in here. And then it's shot with a certain velocity, v, and it's shot into an area where there is a magnetic field. And I'm telling you that the area, or the volume, if you want to think three-dimensionally, where there is a magnetic field is all confined to within the yellow here. Only in the yellow will we have a magnetic field. And I'm going to give you the direction of the magnetic field by, in the corners, drawing a circle with an X, a circle with an X, a circle with an X, a circle with an X. And that is telling you, because we use this notation in grade 11, that the magnetic field is into the page, is into the page. So if I shoot this charged particle, positive Q, if I shoot it into here, you'll see that the angle, theta, the angle between this velocity vector and the magnetic field that is going into the page, the angle between them is 90 degrees and the sine of 90 is 1. So if we go back into this equation, we would get a 1 here, and that would be the maximum amount. So what I'm telling you is that the magnitude of the force is at a maximum when the angle between the magnetic field and the velocity is 90 degrees. There you have it. 1. Now, if we change things around a little bit, and let's say I'm shooting that same charged particle, here's this positively charged particle, Q, and I'm shooting it into the region that has a magnetic field, but now let's say I'm shooting it into the page. That's why I've drawn this red circle with an X. It's telling you that this particle here, positive Q, is shot into the page. Well, the magnetic field is also into the page. So that means that the angle between them is 0. They're parallel to each other. So that means we have sine of 0 degrees, which is 0. So if I go back to this equation and I would put in sine of 0 in here, right? Sine of 0, sine of 0 is 0. It's a minimum. It's 0. It's literally telling you that there is no magnetic force on this charged particle if its direction is in the same direction as the magnetic field? None. So this is a really strange force. This force is literally dependent upon the angle between the magnetic field and the velocity of the charged particle. It can go, the magnetic field can still be there. The charged particle could be moving through it, but it has no effect on it. Boom. Or the magnetic field could still be there, but now we're shooting it at 90 degrees to the magnetic field, and the magnetic force on that charged particle is at a maximum. So this is a different type of force for you because it is so dependent upon the direction of the magnetic field and the direction of the velocity of the charged particle. So we really need to investigate this more fully to try to understand that, and that's what we're going to do. So, direction and magnetism. From grade 11, you should have been realizing you're going to have to use your friend, your right hand, the right hand rule. The right hand rule for this equation right here. Magnetic force on a charged particle is equal to the charge times the velocity with which that charged particle is moving, cross product the magnetic field in which that uh, charged particle is moving within. So you get your right hand out, and this is what you do. You let your thumb be in the direction of the charged particle if the charged particle is positively charged. All right? B goes in the direction of your open hand, and it moves in the direction of your fingertips. So your hand right now should be open. Your thumb points in the direction of the velocity of the positively charged particle. Your fingertips point in the direction of the magnetic field in which that charged particle is moving. And your palm points in the direction of the magnetic force on it. So that means that we would have a force that would be straight out of the page in this situation. That is the right-hand rule for this equation right here. Now you might be asking, well, sure, not all particles are positively charged. Some of them are negatively charged. Good point. If a negatively charged particle is moving in a magnetic field, point your thumb in the opposite direction to its velocity. So if I have a charged particle moving to the right and it's a negatively charged particle moving to the right, I don't point my thumb to the right. I point my thumb to the left. I flip the thumb because it is a negatively charged particle. So what I have here is simulation, and I've given you the link to it. So what's the situation here? Well, there's a magnetic field in here, and I can change. It's in Teslas. Look, I can change the strength of it. I can make it stronger all the way to 10 Teslas, right? Or I can make it non-existent, or I could make it, see how the arrows and axes come about? I could make it negative 10 Teslas, meaning 10 Teslas into the page, no magnetic field, 10 Teslas coming out of the page. And the magnetic field is restricted to this area right here. So let's bring the magnetic field down to 0. And next, we have a charged particle that I can shoot into the magnetic field. Let's do it now without a magnetic field. Watch. See, there's a charged particle. It goes into the area there. So it left here. So I'm going to reset that and clear. So the charged particle is right there, and it's going to be shot into the magnetic field. Now I can change the charge on it. I can make it positive, big, negative, big, or no charge whatsoever. How fast is it moving? Well, I can really make it go into there fast or not as fast. Okay. And what's the mass of it? I can make it very heavy or not too heavy at all. There you have it. So let's put that there. Let's have no charge on it. Let's put, I don't know, some type of magnetic field in there. And let's shoot this into here. All right, no charge on it. If there's no charge on it, there's no magnetic force on it. Remember, QVB. So that doesn't work. So let's put a charge on it. I don't know, something right about there. And let's clear the trace there, and let's shoot it into the magnetic field. Boom. There you have it. It starts to form a circle. And the radius of this circle, show the radius, is 1.45 millimeters. I can change the radius of this circle by changing the strength of the magnetic field. Watch. Now the radius is smaller. I have a really strong magnetic field. I can change the radius by changing how much charge is on there. All right, now I'm going to change the charge on it. Watch. See that? Different radius to the motion here. I can change the velocity here. Let's do one with this velocity. Right? Let's really up the velocity. See how it changes? Reset this. Clear the trace. I can also change the mass, and it's going to affect the trajectory, because remember, mass is all about inertia and how hard it is to change a particle's acceleration and velocity. Watch. So here's one. Now I'm going to make the particle heavier. Watch now. Okay, kind of looks like projectile motion a little bit, doesn't it? All right. So I'll let you play around with this. It's a really good website. You can play around it, and you can see how changing all these variables can change the path, the velocity of the particle, and the magnetic field acting on it. So that's kind of cool. So let's keep this one in mind. All right. All right. Here's another simulation. All right. And it's a charged particle. Let me just play it. There's the charged particle. And you see that the charged particle is in this magnetic field right here. And you see it's definitely undergoing circular motion. It's actually uniform circular motion. There's centripetal acceleration going on here. So let me pause this and reset it. Now, this charged particle right here has the ability to have an initial velocity in the x direction, which is red, and an initial velocity in the z direction, which is blue. Let's bring the initial velocity in blue or z to 0, and I'll play it again. And you'll see that the particle is confined to uniform circular motion. So if you have a charged particle moving in a magnetic field, it is absolutely very possible for it to undergo uniform circular motion. So let me show the magnetic field there. There's the magnetic field here. It's going straight up along Z. And the particle's velocity is shown there. Now I'm going to pause this. So if you were to apply the right-hand rule that I talked about here, your fingertips would be going straight up. Your thumb would point in the direction of this here, and the palm would be pointing towards the center. If you got a force towards the center and the velocity isn't changing, you've got centripetal acceleration and you've got uniform circular motion. Watch. I'm going to play it again. Boom, right there. My fingertips point straight up. My thumb points in the direction of this velocity vector. My palm would be pointing towards the center. It's not speeding up, not slowing down along this path in the x plane here, if you will. This is always its velocity, and the acceleration is always towards the center. We have uniform circular motion being caused by a charged particle being trapped in a uniform magnetic field. So this is what we have right here. I wrote it out for you. A charged particle can be confined to a space with a magnetic field. The charged particle undergoes uniform circular motion, UCM. And we're going to do a question about that. So here's the situation. Right here, I have two charged plates. Positive plate here, negative plate here, and there's a voltage difference across it of 46 volts. And I'm holding a positively charged particle here, it's a proton, with this charge on it, positive 1.6 times 10 to the negative 19 coulombs. There's the mass of the charged particle. And then I'm going to release the charged particle, so it's going to be repelled from the positive plate, attracted to the negative plate, and there's a wee hole in the negative plate that's going to let the positively charged particle go through there. And then it leaves this area here and enters this purple area. And this purple area is where the magnetic field is. And the magnetic field is coming out towards you, out of the page. And it's got 0.20 Tesla out of the page. All right out of the page. And then we need to find out that when this charged particle enters here, and then eventually it gets into uniform circular motion, because of the magnetic force on it, we need to find out the radius of that motion. But before we can find the radius of that motion, we need to find out how fast is it entering the zone of the magnetic field. We need to find out, yeah, it's been sped up here. It started at 0. How fast is it moving when it leaves? That's the next thing we have to do. And here we are back. This is what we're going to do then. Total energy initial is equal to total energy final. So when that proton is on the positive plate, it's not moving, right? It is not moving. That means it has no kinetic energy. It's all electric potential energy, which will equal the charge of the particle times the voltage there, 46 volts. Then it gets to the negative plate. When it gets to the negative plate, the voltage is gone. So there's no electric potential energy there. Actually, this is a good review for you if you're doing the assignment right now. All right. There's no voltage there. It's gone through the 46 volts. But it's picked up a lot of speed, so it has a final velocity as it leaves the electrical field and enters the magnetic field. So what we do here is we rearrange this equation and then we square root it. We plug in charge, the voltage, the mass, we square root, and we get 9.4 times 10 to the 4 meters per second velocity final. And that's the velocity with which it enters the magnetic field. So when it's in here and it's gone into this uniform circular motion, we can say that F net equals ma. And the net force is the magnetic force. That is the only force acting on it. And the magnetic force is causing uniform circular motion, which means that this acceleration will be centripetal acceleration. So we have force magnetic is equal to m times ac. Well, we know the equation for force magnetic. It's q v cross b, and that's going to equal mass times centripetal acceleration. But remember, we can find the magnitude of this. We can find the magnitude of that by saying magnitude of the charge, magnitude of the velocity, magnitude of the magnetic field times the sine of the angle between the velocity and the magnetic field. Well, kids, the magnetic field is coming straight out of the page, and the velocity is to the right. Right here, the velocity would be to the right. Right here, the velocity is at the bottom. It's going straight down. Right here, it's going in uniform circular motion. The velocity is to the left. Right here, when the particle is here, the velocity is upward. It doesn't matter. It's always in the same plane here. So as it's moving around in the circle, yes, the velocity is changing, right? But all of these velocities are in this plane and they will always be 90 degrees to the magnetic field that's out of the plane, that's out of the page. So theta is continually 90 degrees and the sine of 90 degrees is 1. Oops, let me fix that. The sine of 90 is 1. So I can then say Q, velocity final, magnitude of the magnetic field is equal to m. And what's centripetal acceleration's magnitude? Because we're only dealing with magnitudes here. Remember, centripetal acceleration is v squared over r. In this case, the v is vf, the v with which the charged particle entered the magnetic field. So look what happens here. One of the velocity finals cancels out. So we have qb, m velocity final, it's no longer squared, over r. Then we rearrange this and we get an expression for r, and it is equal to 4.9 times 10 to the negative 3 meters. So we have found the radius of the uniform circular motion. Okay, well that's that. That's the end of this lesson. It's a lot of new stuff, so you know, we're going to be patient with each other. I'm going to be patient with you. You're going to be patient with me. We'll get through this. It's a brand new equation. All right. So we'll do the best we can. Actually, maybe today how about I don't give you any questions today? Just reading, watching the video, let this sink in, and then we'll do questions on Monday. Maybe that'll be better. Maybe I should slow down a little bit. Why don't we do that? Might be a good idea. That way you can watch this video a few times, read the textbook, watch the other video I assign, give you a deeper understanding. That probably be a good idea. Anyways, remember, I'm very proud of you. Keep on working. We'll get through this. Have a great weekend, and bye-bye.